Hey, let's do a little practice of writing some expressions that will involve exponents or powers, and and then we'll practice using the order of operations to evaluate those expressions accurately. So there's kind of a lot of words in these examples, and I'll try to go slowly and maybe even sketch out little diagrams, or maybe not. We'll see. I'll try to make it clear. But if the words are confusing, that's right. Don't panic. Um, there's sometimes can be some ambiguity in verbal descriptions of situations, which is why it's nice to write them as algebraic expressions, right? So, uh, okay, the first example is a little bit silly, but it's a semi-real world example. You can imagine something like it um, um, being needing to be solved in the real world. Um, Suppose you have a this awesome cubicle house. It's a cube. So your glass cubicle house, so it's a cube, meaning all of its measurements are the same length, length, width, height. You have this awesome glass cube uh, for a house, and it's 10 meters by 10 meters by 10 meters. In other words, okay, yeah, and next to it you've got a spherical greenhouse uh, with a diameter of 7 meters. So you've got this, it's hard to draw a sphere, but the distance from a point on the sphere to another point straight across from it with a straight line, um, the longest distance, I should say, that you can draw between 2 points is 7 meters. Alright, what is the total volume of these structures? You're just curious. Maybe because you're trying to design an air purification system so that you can sort of recycle your own air in these systems, and you want to know, you got to figure out what's the the volume enclosed by these. I don't know. So the volume of the cubicle house is pretty simple, right? Just 10 cubed, 10 meters cubed, plus the volume of the sphere. So the volume of a sphere is 4/3 pi times the radius cubed. What we have is the diameter, and the diameter is twice what the radius is. So we can just cut this in half. So we can say plus 4/3 times pi. Now our radius is half of 7. So 7 divided by 2 cubed. All right, so let's follow the order of operations here to figure out what the total volume would be. So first, is there any grouping? Yeah, I put this here because it's the whole radius cubed, and we want to indicate that the radius is half of what we're given as the diameter. So I put this in parentheses to indicate that this whole thing needs to be cubed. So yes, grouping. So let's do that first. So 7 divided by 2, we could say is what, 3.5, 3.5. Okay. Well, let me take off the grouping. So we're done. 3.5. This is 3.5 cubed. Okay, so we've got 10 cubed plus 4/3 pi times 3.5 cubed. All right, next up is powers. Do we have any powers? Yes, right here and right here. So let's do those first. So 10 cubed is a 1 with 3 zeros. It's 1,000. So we've got it's 10 times 10 times 10 plus 4/3 pi. Just rewriting what we're not modifying yet. And then 3.5 cubed, I don't know. So I'm going to grab the calculator. 3.5 raised to the power of 3, 42.875. Alright, so we took care of the grouping, we took care of powers. Now do we have any multiplication or division? Yeah, all three of these numbers are being multiplied together. 4/3 times pi times 42.875. So let's go ahead and just multiply those. Um, so times pi, and then times 4/3. Or you can do 4 divided by 3 first and multiply that by pi times 42.875. So we've got 179.59. I'm going to round it to 179.59. We've got 1,000 plus 179.59. Okay, we've taken care of grouping, powers, multiplication, division. Is there any addition and subtraction? Yeah, that's the last bit. So 1,000 plus 179.59 is 1,179.59. Now what are units? We're dealing in meters, and this is a volume, so meters cubed. So altogether, your house plus your sweet greenhouse are 1,179.59 meters cubed. They enclose that much volume. All right, so that wasn't so bad, I don't think. Let's look at this one. This is a little bit more complicated, but not really. Well, maybe. We'll see. A certain bacterium, like the singular of bacteria. Here we go. So here's this little. Here's my very poor diagram. Here's the little nucleus. Maybe there's like some stuff outside the nucleus. Okay. Little oh, it looks like a little sad guy. Anyway, a certain bacterium doubles every half hour, so it grows by 100% every half hour. You inoculate a petri dish with 3 such bacteria. All right, so you've got this petri dish. You're putting 3 in here. You're giving them, you know, a little bacteria food, and you're waiting for 4 hours to let them grow, to multiply. So you wait for 4 hours. The number of bacteria in the dish after 4 hours will be the original number times the sum of 1 and the growth rate, which is raised, the sum, which is raised to the power of the number of growth cycles. So let's translate this. If you've gotten into exponential equations, this might ring a bell. Okay, the number of bacteria in the dish after 4 hours will be the original number. So we started with 3. Okay, the original number 3 times the sum of 1 and the growth rate times the sum of 1. So we're adding 1 and the growth rate. So the growth rate is how quickly it grows. So it doubles every half hour. So if it's doubling, you know, one of them becomes 2. That's a growth rate of 100%. And turning 100% into a number that we can use in an expression, we'd call that 1, right? The decimal version of that is 1. Or you can think of it as, you know, how you move to convert from a percent to a decimal. You move the decimal over. Okay. So times the sum of 1 and the growth rate, which is raised to the power of the number of growth cycles. So the number of growth cycles, it grows every half hour. It doubles every half hour. So if you wait for 4 hours, how many half hours are there in 4 hours? There would be 8. So it doubles 8 times over that period of 4 hours. Okay, there's a little bit of ambiguity here. Times the sum of 1 and the growth rate, which is raised to the power of the number of growth cycles. You might take that to mean that just the growth rate is raised to the power of the number of growth cycles. But I tried to indicate with the comma that this whole thing is a unit. The sum of 1 and the growth rate, which is raised to the power. So the which refers to the sum. But again, there's some ambiguity in language. So if I were talking about raising just the growth rate to the power of the number of growth cycles, I would probably say times the sum of 1 and the growth rate raised to the power of the number of growth cycles. So that this raised right after the rate. Okay. So that's it. So let's go through our order of operations. Grouping. Do we have any grouping? Yeah. We group this to indicate that we're raising this whole sum to the power of 8. So let's do that first. Just rewriting. So 1 plus 1 is 2. This is 3 times 2 to the power of 8. Okay. So we're done with grouping. There's no more grouping. Took care of evaluating what's inside parentheses. Powers, yes. 2 to the power of 8. So let's do that. 2 to the power of 8 is 256. So now our expression is 3 times 256. Okay, so we took care of grouping, took care of powers, multiplication, division. That's all we have left. So let's do 3 times 256 is 768. And then we are done evaluating that. So there's 768 bacteria after your 4 hours. So you start with 3 at this growth rate, which is a pretty modest growth rate for bacteria. After 4 hours, there'd be 768 of them in that petri dish, assuming that they had enough food and everything. So pretty crazy, right? All right, I'll see you later.